Hello and welcome. In this video we are going to take a look at more modeling with differential equations, and we'll take a look at one of the classical problems, which is called the tank problem. We'll do some more model analysis, and we'll also look at something called parameterizations. So mathematical modeling is one of the things I like to spend the most time on because it's the most challenging principles in mathematics, but at the same time it's one of the most important skills to be able to have, especially if you're a scientist, an engineer, a mathematician, etc. This is just something that you need to be able to do, and it takes some time to develop. So to become a strong modeler, of course, one of the most foundational things is to really clearly define the problem. So what is it that you're looking for? What is it that you want to be able to answer? That typically leads us to the unknowns that we have in the problem, so the variables that we're using. Then we often need to have a set of assumptions, something that tells us how things are expected to behave. So if we're dealing with populations, of course populations behave differently than electrical circuits. And we need to know what kinds of things we can assume. So even if we're not experts in the particular field in which we're modeling, then as mathematical modelers, we need to be able to take a set of given assumptions and convert those into something more mathematical. And we often use a lot of dimensional analyses. So units become incredibly important when you're building models. So the easiest way to start is first of all to identify the question. So what are you asking? What is it that you want to determine in the first place? Once you know that, that allows you to then define the variables. And since we're in a differential equations class, we know that we're going to want to be working with differential equations models. So let's take a look at our first tank modeling problem. A 50-gallon drum is initially full of clean water. Water concentrated with 1 pound per gallon enters the drum at a rate of 3 gallons per minute. Salt water leaves or exits the tank so as not to change the volume of liquid in the drum. How much salt will be in the tank after 10 minutes? What is the long-run concentration of salt in the tank? So our question is asking about salt after a period of time. So immediately that tells me, okay, well, I want to model the amount of salt in this tank as a function of time. So I'm going to define some variables. I'm going to say, okay, well, my dependent variable, I'm just going to call it y here, is going to be the amount of salt in the drum. That's what I want to measure. So amount of salt in drum. And we want to specify units because when we write dy dt, we've got to make sure that our units are what they're supposed to be. And so we're measuring salt in pounds, therefore there's no reason why we should convert to a different unit of weight or mass. So that looks good. And then T is going to be, of course, the time since the salt water starts coming in. So we'll just write that. So time since salt water enters drum. And that time looks like it should be measured in minutes since things are happening over the course of minutes in this problem. Of course, we could convert everything to hours, but why would we do that? We're told about measurements that are in minutes, and we're asked questions that are regarding minutes. So to convert to hours and then convert back to minutes would not be highly effective. Now I'm going to build a model for my drum. So I'm not going to draw a big fancy drum, but you can if you want. This is sort of the bathtub analogy. The bathtub analogy says that you have something coming in, you have something going out. We've got to think about what's going in and what's coming out. So imagine that this is the top of our drum. We have liquid entering that drum. So inside of here, we know that this is a 50-gallon drum, so I can label this with 50 gallons. And I also know that y at time 0 is going to be 0. It's initially full of clean water. Initially full of clean water. So I know one of the things I like to put in this is my initial condition that y at time 0 is 0. The amount of salt in the drum when t is 0 pounds. So what I have coming in is I have 1 pound per gallon. So I'm going to write that down here. I'm going to say I have 1 pound per 1 gallon. And I'm going to write my units like this because I want to be able to see how units nicely cancel out. Now the other tidbit I have is that water is entering the drum at 3 gallons per 1 minute. Well, what do I do with those two measurements? One of them, the 1 pound per gallon, that is a concentration. Concentration just means how much weight or mass per volume. So if something is coming in at a rate of 1 pound per gallon, that means for every single gallon of water, there's going to be 1 pound of salt. So imagine that you have a container that contains 1 gallon of water. All right, so there's your 1 gallon. And of course, we're not, it's dissolved inside of here, but let's just pretend for a second that we could separate them. If you could, you would have, for every 1 gallon, you would have 1 pound of salt. Okay, so that's essentially what we're saying here. Now, we do need to define these variables because dy dt, its units are going to be in pounds per minute. So when I look at the net inflow rate, which is the rate in, or the rate of salt in, minus the rate at which salt runs out. So this is just like thinking about water entering a bathtub. The net rate at which your tub is either filling or draining is a function of, okay, well, if your tub is filling at 10 gallons per minute and it's draining at 7 gallons per minute, then 10 gallons per minute coming in minus 7 gallons per minute coming out tells me that every minute I should see 3 more gallons in net inside of that tub. So no different here, it just happens to be pounds of salt per minute instead of gallons per minute. So the rate coming in has to be in pounds per minute. Otherwise, there's no other way that I could subtract 2 units and end up with pounds per minute unless they're both in pounds per minute. So that's going to be crucial. This has to be in pounds per minute, and this has to be in pounds per minute, so that when we subtract them, we still end up with pounds per minute. Here I have pounds per gallon. How many pounds of salt will be added to each gallon? Here's how many gallons are coming in each minute. But wait a minute, so if I look at the units here, if I multiply these together, I'll end up with pounds over minutes. And this should make sense because if I have 1 pound every gallon, and I have 3 gallons coming in every minute, that means I'm going to have 3 pounds for each of those 3 gallons across that entire minute. So it's not surprising then that we would have 3 pounds per 1 minute. Now again, this guy here is called the concentration. This is called the concentration. And this is what I like to just call the flow rate. The flow rate. And all that means is how fast the clean, unadulterated water is coming in. And the concentration is at what dose am I putting in this particular chemical. Now what I have coming out gets a little bit more complicated because initially we might think that, well, if you put in 3 pounds and you're pushing the same amount of water in as you are out, because it says here salt water leaves/exits the tank so as not to change the volume of liquid in the drum, we do know that the flow rate out is also going to be 3 gallons per minute. And this way, if you have 10 gallons per minute coming into your tub and 10 gallons per minute leaving your tub, then that water level should never change. It should remain at whatever it was when you started this process. But here's the thing. Those 3 pounds, we're going to make a key assumption here. And that key assumption, and I'm going to put this off to the side, is first of all that the water is always well mixed. So the tank, the drum water, or drum liquid, is always, or instantly well mixed. We'll use that word. And what we mean by that is basically imagine or pretend that you have some sort of propeller in here that just continuously mixes the salt with the water. So you don't have like pockets or patches in here where, let's say, all the salt kind of condenses in this corner and nothing's inside. We're assuming that the second that salt comes in, it's instantly well mixed with everything in there. Now, whether that's a good assumption or not really depends on the context. If this is a lake, then it's probably not a great assumption because there's probably not something spinning it. But if this drum is being shaken, or if there is something in there stirring it up constantly, then it is a good assumption. So we are going to make that assumption in this problem. Otherwise, we're going to have a really difficult time trying to argue about, okay, well, where is the salt? How much is really coming out? So now that we have that underway, if the 3 pounds get mixed in with that, and after 1 minute, you might say, okay, well, 3 pounds have basically made their way in. But they haven't necessarily made their way out because only 3 gallons are coming out every minute. But this 3 pounds that's mixed into this 50 gallons is equally dissolved inside of here all over the place. And so the 3 gallons that come out are just a really lightly concentrated version of what went in, right? Because 3 pounds is a lot, but not in 50 gallons. So all of that salt doesn't make its way out each minute. And therefore, it's a little bit more difficult to say, well, how many pounds of salt are inside of that tank? And this is where we get to use our variable. The variable that represents how much salt is in the tank is Y. That's the amount of salt in the drum. So in following the same procedure, here we have our flow rate. Now we need a concentration. And the only thing that we do know is that there are inside of this tank, what's coming out is concentrated with Y pounds of salt, right? Because that's how much salt is in that drum. It's not like here what's coming in is consistently, somebody's controlling the dial and they're saying only 1 pound is going to be added for every 1 gallon that comes in. But there are already Y pounds in here and there are 50 gallons. So the concentration of salt in the tank is Y pounds mixed into 50 gallons. This is a much safer bet than trying to say, well, it's 2.9 or it's 2.8 or it's 3. We just don't know. And now that we have this, we're pretty much ready to build our model. Our dy dt is going to equal the rate in, which is, we said 3. And I'm just going to write 3. I'm not going to use the units now because it's already in pounds per minute. Now down here we'll have the same dimensional analysis because here the gallons will cancel and will be in pounds per minute, except in this context we'll have Y times 3, or 3Y pounds, divided by 50 times 1, which is 50 minutes. So this is in 3Y pounds per 50 minutes. It might seem weird at first because you have a variable in your unit, but that's okay. It's just an unknown quantity. And so this will be 3 minus 3y over 50 as our differential equation. And so this is our dy dt. Okay, so now that we have the model, we're ready to analyze the model. We want to solve it. We want to say how much salt will be in the tank after 10 minutes. And we can't really answer that right now. We just know how fast the salt is accumulating. So we do need to solve this differential equation. And in order to do that, we're going to use our technique of separation of variables, because we see that this guy depends on y and not on t, and we can write it as a product of some function of t and some function of y. So what I'll do is I'll say dy dt equals, and we have 3 minus, I'll just write this as 3/50ths y, make it a little bit easier to work with, and I'll multiply this by 1. So we can think of this as our h of y, and we can think of this as our g of t, and that means this is a separable differential equation, so we can divide both sides by 3 minus 3/50ths y, and that's times dy dt equals 1. So now we're going to integrate, and so we're going to integrate with respect to t. Remember, this cool thing happens here. This whole method just works out because of the fact that those dt's change your variable of integration, and we now have something that can be integrated using our Calc 2 techniques. So let's go ahead and integrate this in Wolfram alpha. And so here we are with that integral. Now, of course, if you integrate this by hand, your answer may look slightly different depending on what you factored out before you took the integral, etc. But, Wolfram does a good job of compacting it down as far as possible. So when you look at this and you think, well, I thought the argument of log should involve the denominator, looks like a 3 was factored out, or a 3/50ths was factored out from this expression. So in any case, our integral, trailing back down here, is the left-hand side is going to be negative 50 thirds natural log. Don't forget that that's what comes out of Wolfram alpha. 50 minus y equals, and the integral of 1 is t plus c. So now we can isolate y, so we're going to multiply both sides by negative 3/50ths. And the thing to remember is that when we do that, we multiply both terms by the negative 3/50ths. But when you multiply an arbitrary constant by a constant, it remains an arbitrary constant. So I'm just going to use c. If you want to use c1, you're welcome to. We're never really going to need to trace back and figure out what the original constant was. So we're okay. We're going to exponentiate both sides. E to the power of the left equals e to the power of the right. And on the left, we'll have 50 minus y equals, and then if we factor out, break this apart into e to the negative 3/50ths t times e to the c, we'll have k e to the negative 3/50ths t. And then we'll subtract 50, divide by negative 1, and if we divide k by negative 1, we can just leave it as k, so we'll have k e to the negative 3/50ths t. We subtract the 50, but then we multiply by a negative 1, so it'll be plus 50 over on this side. Now, if you want to leave this as negative k, that's fine too, but remember, k is an arbitrary constant, so if you put a negative sign in here, the value that you get for k itself will be the opposite of the right sign. If you had the minus here, and k came out to be, say, 50 right here, but here it became negative 50, because negative 50 is still equal to positive 50. So it's just easier to write it this way. And now we can satisfy that initial condition. We said that initially our ordered pair is 0, 0. So y is 0 at time 0. So this will become k plus 50, which leads to k equals negative 50. And our final solution will be y equals negative 50 e to the negative 3/50ths t. Plus 50. And now we wanted to know what's going to happen after 10 minutes. So that's a fairly easy assessment. We just have to calculate y of 50. Now I'm going to go over to Desmos and I'm going to graph this solution just so I can answer both these questions at the same time. So the questions, if you recall, were how much salt will be in the tank after 10 minutes and what is the long run concentration of salt in the tank. Okay, so here it's saying how much salt, so how many pounds of salt. But the next question is asking how many pounds per gallon will there be in the long run? How many pounds per gallon? So let's do this in Desmos. All right, so here I have that function graphed. I don't like the current window, so I'm going to zoom out a bit to see what's going on. And it does actually look like over time, at first there's a rapid growth in the amount of salt. Whoops, didn't want to do that. There's a rapid growth in the amount of salt. So on the x-axis we have time measured in minutes, and on the y-axis we have the amount of salt in drum measured in pounds. Good deal. So now that we're looking at that, so we can figure out what's happening after 10 minutes. So after 10 minutes, I can actually plot this ordered pair. I can say I've called my function s of x to stand for salt, and I can't use t, so I'll just do 10 comma s of 10. Now what that does is actually plots an ordered pair, and because I've named the function s, when I calculate s of 10, that physically puts 10 in for x for me. And so this is the ordered pair corresponding to what salt would be at time 10. So at time 10, there will be 22.559 pounds of salt in that tank. Now we want to know what the concentration will be. So this is, right here, I'm going to insert a note and I'm going to say this is the amount of salt function, S of x. But if I want to get the concentration of salt, concentration is the amount divided by the volume. So to get the concentration, if you put in a quote, if you just insert a quote, it will automatically convert this to a text box. Concentration of salt function, well, that's going to be S of x, the amount of salt, divided by how many gallons are inside of that drum, which is 50. So if I just take S of x and divide it by 50, you'll notice that it plots a very shallow function because we're taking 1/50th of this curve up here. And if we do that, then we can see along this curve that it seems to be inching closer and closer and closer to about 1. So you can see that after about 83 minutes, we're approaching a concentration of 0.993 pounds per gallon. Now let me make this go out a little bit further so we can see that more distinctly. If I went to time 200, you can see that by then both the amount have flattened out. So I'm reaching about 50 pounds. And 50 pounds in 50 gallons is about 1 pound per gallon. You can see that here that we've reached a concentration of about 1 pound per gallon. So it appears that the concentration inside the tank actually reaches the concentration of salt being added to the tank, which kind of makes sense. The concentration inside the tank can never exceed the concentration of salt that you're putting inside the tank. So let me graph just the horizontal line y equals 1, and you can see here that that black line is the asymptote for the concentration. So even though we didn't solve for concentration, we solved for the amount of salt, we just had to divide it by volume to get the concentration of salt. So that about concludes our analysis for this question. Let's look at another problem that involves this next problem. We have a very similar situation, but here we have 30 grams of a toxic substance entering a 10,000 gallon pond each minute through waste runoff from a chemical company. Now, that just means that we have sort of a larger drum here. This is the same kind of concept, but now our tank, our drum, is actually a lake. So when we talk about tank problems, it doesn't actually have to be a physical container. It could be something like a lake or a river, or the human body can be thought about as a tank. So to keep the water level constant in the pond, water leaves the pond through a stream at 20 gallons per minute. The pond initially has clean water. When will the amount of the substance reach a dangerous concentration threshold of 5 grams per gallon? So we're going to model it as before. We're going to think about what it is that we want to ask. Now, we never model concentration. Concentration is just the amount divided by the volume. So as long as we know the volume, we can figure out the concentration later on. We always want to define our variables as amounts. It's just too tricky to try to get into concentrations. So let y be the amount of toxic substance, in pond. Well, that's measured in grams. And t is I'm just going to say time here, but we know this is the time since the substance begins polluting this pond. This is measured in minutes. And so one thing that we should point out is that dy dt will have units of grams per minute. Now the one nice thing here is I'm already told how many grams are entering per minute. So when I draw my sort of my bathtub analogy set up here, what's coming in is strictly given to me as 30 grams per 1 minute. Now that's already in the correct units of the inflow rate, and remember we're looking at inflow of substance minus the outflow of the substance. So here they don't tell me what the concentration is, so I don't have to multiply the units together like I did before. But one interesting thing is that if we know that 50 gallons or 20 gallons per minute are leaving in order to keep the water level constant, that must mean that there's 20 gallons per minute coming in as well. Now again, this is not something that you need to know. for moving forward with this problem, but this 30 grams per minute has essentially already been figured out for us. So I have to ask myself here, what if I wanted to know at what concentration the salt or the substance is coming into the pond? I could just take 30 divided by 20, which is actually 1.5. So if I really wanted to know all those details for some reason, I could say, well, this would have to be 1.5 grams per 1 gallon in order for these two to multiply and give me 30 grams per minute. So again, just sometimes you get information that's you don't need to put together, it's already put together for you. And what's coming out? So once again, the concentration inside is going to be, there's going to be Y grams dissolved in 10,000 gallons. And so again, we have grams over gallons, and that's going to get multiplied by gallons per minute, which is 20 gallons per minute. And our dimensional analysis will tell us that we are in grams per minute. So this will come out to 20Y over 10,000. And again, that's now in grams per minute. I'm also going to go ahead and reduce this fraction a little bit just to make it simpler. So this is 2 thousandths, and which is 1/500th. So I can write this as 1/500th Y. That'll just make it a little bit easier to work with. And so now our dy dt model is going to be the difference between our inflow and our outflow. Our inflow is 1.5 grams per minute. 30 grams per minute. 30 grams per minute minus 1/500th Y grams per minute coming out. There is my model, my initial value problem. So now coupled with my initial condition, I could have said over here in this box, this is 10,000 gallons with no substance initially present. And so there is my IVP, my initial value problem. And I can now begin doing my calculus on this. So once again, this is a separable differential equation. I know that because there's no t in the equation, for 1, and if I factor this out into 1 times 30 minus 1/500th Y, and 1/500th is actually 1/5 would be 0.2, so this would be 0.002. That's an exact number, so I can leave this as 0.002. It'll make it a little bit easier to write down. So I'm going to divide over by the h of y, which is 1 over 30 minus 0.002y times dy dt equals 1. And now when I integrate both sides with respect to t, these will cancel, and now I will go ahead and integrate that with Wolfram alpha. And there you can see the result. So this will integrate to be negative 500 ln of 30 minus 0.002y equals t plus c. And now I can divide by negative 500. So that will leave me with natural log of 30 minus 0.002y equals, so this will be negative 1/500th t, or negative 0.002 t. And then when I divide c by negative 500, that's an arbitrary constant divided by a constant, so I can just leave that as plus c. Now I'll exponentiate and make this ke to the negative 0.002 t, subtract 30 and divide by negative 0.002, which leaves me with ke to the negative 0.002 t. Remember, because when we divide k by a constant, it remains an arbitrary constant. And so when we subtract 30 and divide it by negative 0.002, we get plus 15,000 over here. And now we can solve for our initial condition. I'm just going to make the claim here that when you plug in 0 for y and 0 for t, you're going to get k equals negative 15,000. And so our final equation will be negative 15,000 e to the negative 0.002 t plus 15,000. And you can go ahead and verify just to be sure in your own mind what that's going to be, negative 15,000. Let's go ahead and graph this. Now remember, this gives me the amount. This is the amount as a function of minutes or time. And so if I want to know the concentration, remember I'm going to have to divide this by the amount of volume in that pond. Because I want to know not when does the amount of this toxic substance reach 5 grams, but when is the concentration of the substance 5 grams per gallon. So let's go ahead and analyze that. And so we'll just go ahead and plop this in to our graph. So we have negative 15,000 e to the negative 0.002x plus 15,000. Now I want to give this a function name. I'll just call this s of x again for substance. And now I probably should adjust my axes here. So this is time in minutes amount of substance. And not in the drum, but in the pond. And that's measured in grams. Okay, so I see first of all, I can verify visually, and we should have done this in the last graph as well, but at time 0, there's nothing in the pond. And as we begin to zoom out, we're going to get an ugly looking window, but that sort of flattens off all of a sudden. So I can tweak that a little bit. I see I probably don't want to go beyond time about 3,000 or so. So I'll just go ahead and take my x-axis from 0 to 3,000. And there we go. So that's a pretty good graph of the image. Now again, this is the amount that's inside of there. So clearly we reach 5 grams total very, very rapidly. That happens almost instantly just based on what's coming in each day. So if I want the concentration, which is going to be s of x divided by 15,000, not 15,000, 10,000, that's the amount of water inside that tank. So if I take s of x and divide it by 10,000, now that's going to be very, very flat. That's just because the number of grams ends up being very large. But let me go ahead and zoom back into the standard zoom, and you can see the concentration is actually really low. So let me change my y-axis from something like 0 to, I'll start off with 0.1, and that looks a little too flat. Let me go 0.01. All right, well now we're getting somewhere. And I can start to slowly zoom out and see what that's going to look like. And I can see that that's starting to flatten out nicely over time. And I can get in here and kind of tweak this a little bit. I don't want to go quite up to 4. I can see that that's going to be well below 2. So now I can change my x-axis to go to, let's say, there's 1,000, there's 10,000, probably up to about 5,000 minutes. There we go. That looks pretty good. And I can see that that concentration is approaching 1.5 grams per gallon. And that's pretty interesting because guess what? What we calculated back here was that in order for 30 grams to be entering per minute, without the volume changing, knowing that 20 gallons per minute are coming out, we were able to solve for the concentration coming in as 1.5 grams per gallon. So that's kind of funny, right? Because this is asking for when will the amount of the substance reach a dangerous concentration threshold of 5 grams per gallon? Well, we could have answered that question just by looking at the model itself. And so part of the purpose of this problem is we went through a pretty sophisticated analysis, but we could have answered that question had we thought about it a little bit more at the beginning, saying, well, the concentration coming in is only 1.5 grams per gallon. Therefore, this threshold will never occur. Even though that toxic substance is entering, it will never be at a dangerous level. But we answered the question, we just did a lot of work to do it. So sometimes when you think about problems a little bit ahead of time, you save yourself a lot of energy. So units can reveal just as much sometimes as an actual calculus solution method. Now let's reconsider this scenario, but let's instead suppose that p grams of the toxic substance were to enter the pond. Up here we assume that p was equal to 30, and down here we want to figure out what the largest value of P would be so that we would never reach 5 grams per gallon, but that we could get infinitesimally close to that value. So in other words, what's the largest concentration of this substance you can have so that it never reaches? So like, what's the upper threshold? Anything below P grams should result in a concentration that never reaches 5 grams per gallon. So let's look at the simpler analysis first, and then we'll also do the calculus version of the analysis, because sometimes you cannot do the simpler version. So in our tank model, we assumed that there are P grams per gallon coming in, per minute. And we probably should have said per minute here, but so we have P grams per 1 minute coming in. And the analysis we did above was that this number is going to be the product of the concentration and the flow rate. And if we look at how many gallons per minute are coming in, we already know that that's 20. The reason we know that's 20 is because there's 20 gallons of water leaving the pond per minute. In order for the volume of the pond to never change, you'd also have to have 20 gallons per minute coming in. Well, in order for us to exactly reach 5 grams, right, to get exactly 5 grams per gallon, we would have to be injecting 5 grams per gallon of this toxic substance in the first place. So anything below 5 grams per gallon, you're never going to reach the concentration of 5 grams per gallon. But the question is, what's the largest value of P? 20 times 5, this will give me grams per minute. This will come out to 100 grams per minute. So that means that the largest value of P is going to be 100. That's the easiest way to determine that value. But let's go ahead and do it the calculus way as well. How do you work with this symbol? Because in the next couple of problems, we're going to have to work with this symbol. So our model dy dt, without rebuilding the whole thing again, is going to be the rate of grams per minute coming in, which is P, minus what's coming out, which we've already established to be 0.002y. So the only thing that's changed in this problem is what's coming in. And now if we went about solving this the exact same way, where we wrote this as a product of an h of y multiplied by a g of t, and we divided both sides by that. So we'd have 1 over p minus 0.002y, dy dt equals 1. And now when we integrate both sides with respect to t, you notice that it ends up being the same problem. The only difference here is that now we have this constant p. I say, well, how do I deal with the constant p? Well, it's a constant, so you treat it as if it were a number. When we go to Wolfram alpha, in place of putting in what we had there before, which was 30, we're going to put in p. And Wolfram alpha will know that if we're integrating with respect to y, to treat p as if it were a constant. So here we have what that comes out to, which is a very similar integral, once again, negative 500 natural log of p minus 0.002y equals t plus c. Again, carrying out very similar steps. Natural log of p minus 0.002y equals negative 0.002t plus c. That's the same thing we got before. And when we exponentiate and divide by 0.002, what we'll end up with is k e to the negative 0.002t plus p over 0.002. Okay, so this p before was our 30 divided by 0.002, which came out to 15,000, but now we don't have that value. So you can see how much work this involves already, even symbolically. And now we would plug in our initial conditions, and we would get k equals negative p over 0.002. So again, you can go ahead and verify that, plug in 0 for y, plug in 0 for t, solve for k. And now our final equation ends up being y equals negative p over 0.002 e to the negative 0.002t plus p over 0.002. Okay, so if we wanted to now work with this equation, we could go into Desmos and we could, in place of the symbol p, put the symbol p. And I'll show you exactly how to do that. So let's say here we have s of x equals, and we have negative p, and you can see that right away when you put in a symbol other than x and y, that you have this button that says add slider. We'll come back to that in a second. So divide that by 0.002, e to the negative 0.002x plus p over 0.002. So now I'm going to press this button called add slider. And what that does is, first of all, it starts by setting a default value, and it always sets that slider to start by default between negative 10 and 10. You can see that as I change that value of p, it really shifts that curve quite a bit. In fact, let me go ahead and zoom out far enough so you can kind of see that it's going to look much like the same function, but as I change that value of p, you can see it changes the equilibrium amount, the value at which the amount of toxic substance in the pond stabilizes to. So, of course, negative values don't really make sense because you're not taking away substance, you're adding substance. So you come up to this gearbox and you press edit. Now you can change this to be between whatever values you want. Now I'm just going to go, because I already know something about this, I'm going to go up to 100. The reason I'm going up to 100 is because we have already solved and we found that p equals 100 is the right value. But you would normally have to play around with the slider quite a bit to see what effect it has. So rather than to graph s of x, I don't want to look at the total amount of the substance in the pond, I want to look at the concentration of it. So I'm not really even interested in this curve here. What I'm really interested in is s of x divided by the volume, which is 10,000. That's going to produce a really flat curve. I'm just going to come over here and change my y-axis from 0, and I'm going to go up to 5. And the reason I'm going to go up to 5 is because 5 is the maximum allowable concentration that I want to reach. And of course, as you put more grams per minute into that pond, that means you're adding a higher concentration. And as soon as that amount reaches or starts to stabilize, see now it's getting really close, it never quite reaches 5 here. It's about 4.95 is where this one stabilizes to. But if I make this 100, you now see that the asymptote is exactly at y equals 5. So we get the same answer this way as well. So y equals 5. And that's when p is equal to 100. Another thing you can do in here, by the way, is when you change your settings, you can actually change this to like a dotted line just to show that that's your asymptote. And so we've answered this question. We found that if p equals 100, the concentration of substance will approach 5 grams per gallon in the long run. And if we just want to be sure, we can even insert a table in here just to say, well, I see that it reaches 5 here, but I want to be ultimately sure. So I'm going to plot s of x. Now, you can't just do s of x. X is a variable. x1 is the name of the value that goes in the left column here. So if I just type in a 1, it'll automatically subscript it. And now I can look at it at time 10. Oh, and I want to take s of x1 and divide it by 10,000. So you can do that in this table as well. And now at time 100, at time 1,000, at time 10,000, you can see that progressively these concentrations are approaching 5. And so after time 100,000. Now if you don't want to show these points on the curve itself, you see that it's actually putting them on there, you can uncheck that box. And just to add closure to this problem, we state that if p is less than 100, 5 grams per 1 gallon will never be reached in the pond. What we've done here is we've parameterized our model. Parameter is just a value. It's a value that represents a constant, but that constant can be different in different scenarios. So in one pond, that parameter could be 30, but in another pond, it could be a constant 20. The advantage of working with parameters is that really it enables us to study a model at a broader level we can investigate the effects of this parameter. Basically see how does this value affect the long-run behavior of our model. And also we can do a sensitivity analysis or stability analysis and figure out, does changing that parameter really affect the long-run behavior of the model? In this case it did, and the one thing that we noticed was that the peak of this curve got higher and higher as we increased the value of p. So we knew something about this model that we maybe wouldn't have known if we had just stuck with the value of p equals 30. We had to do some really general thinking here. And you see that we did end up getting 100 just by a dimensional analysis, but by solving this, we could now also see the behavior of the curve itself. And that was something powerful that you just can't get even by using the dimensional analysis. But of course, we could have answered the question in 30 seconds instead of 10 minutes. So let's look at one more situation, actually two more situations, and then we'll go ahead and call it wraps. Suppose a population of salmon reproduces at a rate of 25% per year. Fishing is allowed in the stream at a rate of R fish per year. If the stream is initially stocked with 500,000 salmon, how many fish can be caught so as to maintain a sustainable fish population? All right, so clearly we're modeling fish equals the number of salmon, and t is, we'll just say, again, time since we start the study, but we'll just go ahead and say time, and this is measured in years. So that already tells me that my model is going to have to be in units of salmon per year. Now, because there's a reproduction rate of 25% per year, another way we could think about this is that 25, every single fish in the population will on average produce 0.25 fish per, baby salmon per year. And I don't know if this is a valid figure. I've just created this. I'm sure if you were an ecologist and studying salmon, you'd know this figure better than I do. So let's draw our black box model. We know we have reproduction, which is causing the number of salmon in here, which is initially 500,000. So there are 500,000 salmon swimming in here, but we are putting more in via reproduction, and it's 25% per year. So that means that of the salmon, on average, that each of them will produce 0.25 baby salmon, which will now enter or be the inflow rate of our population. And this is going to be in new salmon per year. So that's the unit that I want. Now what I have coming out is just the fishing. Now we're not taking into account death or migration, etc. We're just saying that there are R salmon per year exiting this model. And therefore our dy dt is going to be the difference between those, which is 0.25y minus R. And you can see that we have that value of R right now that is we have that value of R in our model just like we did a different valued parameter in our previous problem. Now once again, if I write this as R is a constant, Y is my dependent variable, so the right hand side only involves the dependent variable. If I write this as 1 times that, then I can think about this as my function of t, and I can think about this other one as my function of y, and so that means the equation is separable. So divide over 0.25y minus r. And I'm going to skip a step here to see if you believe me on this and just go ahead and verify that this integral will become this integral right here. And once I integrate this with Wolfram alpha, we can see that we get 4 natural log y minus 4r. So 4 ln y minus 4r. Again, if you had integrated this by hand, you may end up with a different answer. Wolfram alpha does some simplifications that make hopefully our lives a little bit easier. And now we multiply both sides by 0.25 or divide by 4, same thing. Natural log of y minus 4r equals 0.25t. And if we divide c by 4, that's still just an arbitrary constant. Exponentiate y minus 4r equals k e to the 0.25t, and add 4r, we get y equals k e to the 0.25t plus 4r. Now for our initial condition, we're going to put in 500,000 for the number of salmon, at time 0. And so that's going to give us 500,000 equals k plus 4r. So that means k is going to equal 500,000 minus 4r. And our final model will be y equals k, which is 500,000 minus 4r, e to the 0.25t plus 4r. And now this is the number of salmon. This is the model for the number of salmon in our lake, our pond, excuse me, or wherever, stream, whatever it is we're talking about. So with that being said, we now can take a look at this for various values of r, and we want to determine how many fish can be caught so as to maintain a sustainable fish population. Well, we could probably agree that what that means is that we don't want the population to decline. So we want the population to either continue increasing or to flatten off. So let's go ahead and take a look at this in Desmos. So here we go. I've got that model in there. It's again asking me if I want to insert a slider for R, which I will go ahead and do. I'm going to go ahead and default that. I know that I can't fish fewer than 0. And maybe I'll just start off by going up to 500, and we'll see where that leads us. And then I might need to adjust that. So I'll click Done. And so we know that the number of fish initially is 500,000. So we're going to need our y-axis to go at least up to that. I'm going to go 600,000. There we go. And that allows me to zoom out. Now, if you're only fishing out one fish per year, clearly that's okay. We see that that population is going to explode based on the reproduction rate. And again, our assumptions in this model are only 2. That the salmon reproduce and that there's fishing. So nothing else. There's no disease. We're not accounting for anything like that because that's going to make our model instantly more complex. Now what I should see as I start to change this value of r is progressively that curve should kind of start to change or flatten. Now it's kind of hard to see because maybe with 500,000 fish initially present, even fishing 500 of them is probably not too big of a deal. So let me go up to 500,000 on that, because I know if I fished all of them out, then clearly they would die off very fast, right? Within just over the course of a year, because there's some reproduction going on. They last a little bit longer than a year, but not very long beyond a year. So as I decrease that rate of fishing, you can see that it takes, still the fish are going into extinction, but now it's taking a lot longer for that to happen. Now it's taking almost 2 years for them to go extinct. And eventually, you can see that this curve is starting to do something interesting. It flattens off. At 125,000 fish, nothing happens at all. That is, the rate at which we're fishing must be equal to the rate at which they're reproducing. So 25% of 500,000, if you think about it, is going to be 125,000. So if the rate at which they're reproducing is equal to the rate at which they're being fished, then obviously there's not going to be any change in the population. I would call this sustainable. That in other words, that if these are the only 2 things going on, fishing and reproduction, that you could fish 125,000 of them and still keep them intact. Now anything less than that would be desirable, right? Because 124,000 now not only allows you to fish at that rate, but also ensures that the population continues to grow. And depending on your ecological stance and what your objective is, you also don't want the population to become overpopulated. So in this case, the salmon population is going to blow up incredibly. But at 125,000, we are perfectly in good shape. And to wrap up this problem, we'll just say that by allowing fishing at a rate of 125,000 fish per year, the salmon population will remain stable at 500,000 salmon. So any fishing rate below 125,000, we're in good shape. And now we can even determine how many permits we need to issue, for example. So if we allow each fisherman a maximum of 10 salmon a year, then we could say, well, that would allow us to issue 125,000 salmon per year divided by 10 salmon per license. You'd have to you'd be able to give out 12,500 permits for that particular stream. All right, we'll take a look at one more problem, and in the next lesson we'll take a look at that 125,000 and how we could think about that 125,000 without having to go through this whole solution process. Some other techniques in analyzing differential equations. In this last problem, suppose you take out a loan at 1% per month. You make monthly payments of P dollars. What is the minimum required payment so that you can pay off a loan of $10,000? Okay, so first of all, the thing that we should notice is that if we're being charged interest and we're making a payment, if the amount of interest that we're being incurred, or it's being incurred on our account, is greater than the payment that we're making, our loan balance is going to go up. But if our loan interest amount is smaller than our payment, then our balance will go down. So let's draw our black box model here just to see that this is another bathtub analogy problem. So we have our balance in here, which we'll just say y equals loan balance, to be measured in dollars, and t will be time since you took out the loan, measured in months. Since we're in months, we're going to stay in months. If you want to convert to years, you can convert to years, but not necessary. So y of 0, the balance at time 0, is $10,000. And what we have coming in is 1% interest. 1% is always being taken off of your loan balance. So 1% of whatever your loan balance is how much the bank will charge you. So the first month, 1% of 10,000 is going to be 100. And so if that's the case, then that means I'm going to have $100 of interest in my first month. Now what's coming out is I'm going to be paying this thing off. I'm going to be draining this balance tub at a rate of P dollars per month. And notice that our units here have to be in dollars per month. So dy dt will be the rate in minus the rate out. And once again, we'll solve this. So see if you agree with me here, and go ahead and work this off to the side, or go ahead and pause the video and do this on your own. But here's the integral that we'll ultimately have to take care of. And once we do that, I'll just go ahead and do this in my head, but I think we're going to come out with 100 times the natural log of 0.01y minus p equals t plus c. And when you divide by 100, you'll have, let's see, y equals, this will be k e to the 0.01t. And let's see, then we'll add p and divide by 0.01. So we'll have plus p divided by 0.01. Plugging in our initial condition, we should get that k is equal to 10,000 minus p over 0.01. Again, I'll let you work through those details. But here we have, finally, y equals 10,000 minus p over 0.01 e to the 0.01t plus p over 0.01. And now we're ready to analyze the model. So we want to know what's the lowest payment that we have to make in order to pay this balance off. All right, so we'll go ahead and insert that slider for P. We're talking payments here, so it doesn't make sense to make less than a $0 payment. And I'm going to go all the way up to maybe $500 payment. It's a $10,000 loan. You can't be making payments of more than $500 a month on something like that. All right, let's go ahead and see. So our initial balance we know is up here at 10,000, so I'm going to have to set my balance higher than that just to be able to see the curve. And what we have going on here is, well, if I make a $1 a month payment, then my balance is just going to continue to soar. I'm not making payments to keep up with the interest alone. So this is what we often call a reverse amortization, which means that instead of reducing the balance, I'm increasing it. And as we increase this payment, we should see that our balance is still increasing because I'm not making a big enough payment yet. But eventually, if I make a big enough payment, oh, look at that, $100. If I make a $100 payment, my balance will never change. Well, that must mean that the interest on $10,000 is $100. And if I'm paying $100 and they're charging me $100, then I'm never changing the balance. And that's not good either, right? But if I change this to $101 or $103, you can see that over time, and it takes a long, long time, in that case, I'll be paying this loan off for 354 months, which is almost a 30-year loan of $10,000. That's excessively large. But you can see what happens if I make payments of close to $500. I can get that balance paid off in about 22 months. If I make it closer to $300, let's say, then that's going to take me about 41 months to pay off. But if I make that payment equal to 100, notice that at p equals 100, the function goes from increasing to non-increasing, non-decreasing to decreasing. That's going to be something we're going to keep in mind as we move forward in our study of differential equations. So there we go. So this is our time in months, and this is our balance in dollars. And we'll just go ahead and end this by saying a payment of anything greater than p equals $100 per month will allow the balance to ultimately be paid off. So in this video, to recap, we've looked at some tank problems, we've worked with the bathtub analogy some more, and we've begun to look at parameterizing our models to conduct more robust, powerful analyses. In the next lesson, we will get into how could we have solved some of these questions a little bit more simply using some other techniques.